Right. So, the first thing concerns the starting value of the weights, right. So, you have all this alphas and betas, you have this whole set of parameters in a neural network, right. So, we talked about gradient descent, but gradient descent starts at some point in the weight space, right. So, you need to have an initial guess for what your alpha and your betas should be, right. So, what should you do? What is a good guess? Set them all to 1, is it? Yeah. So, setting all of them to the same value, whether it is 1 or sometimes people suggest 0, right, setting all of them to the same value is usually not a good choice, right. More often than not, you will end up in some weird part of your gradient space and you will find it hard to get out, right. It is very rare that you are going to come up with a actual solution where all the weights are the same, right. So, if you are going to start off with a solution where all the weights are same, right, it is going to be hard to specialize, right. So, typically what you do is you do use random initialization, but there is one more constraint. Wow, you must be feeling really lonely. One more constraint to the random initialization. So, what do you think that could be the constraint? Yeah, of course, you do not really want to have infinite weights. Yeah, so but then what should the min and max be? So, you really want your weights to be rather small. Okay. So, just think about what is the implication of having really small weights. What is the implication of having really small weights? So, you remember your sigmoid, right. So, if your weights are really small, where do you expect the outputs to lie? You know, your alpha transpose x or your beta transpose z will lie somewhere in this region, because this is where 0 is, right. So, this is 0.5 or 0 depending on whether you are using tan h or the sigmoid. So, if you are using the sigmoid, so right, so around 0 you will have this 0.5. So, if you look at this region, this is almost a linear region, correct. This is almost a linear region. So, I would really like to start off my network so that most of the outputs of the neurons are in the linear region. Why is that? Can you think of it? I mean, you have enough information to answer this question. The gradient will be larger, right. So, the gradient will be larger if you are somewhere around here. So, even small changes in the input space or small changes in the weights will actually cause a large change in the output, right. So, if you end up going somewhere here or somewhere here, right, you can see that you are already saturated, right. So, you really have to drag yourself all the way here to see any change, right. So, if you are somewhere in the middle, you are more sensitive, right, to what the input, right, you are more sensitive to the weight changes, right. So, all of this helps you learn more rapidly. So, this is one of the reasons you start off with random initializations around 0. So, of course, you can't make everything 0, but then that will put you in a very weird part of the search space, right. So, it is good to have some kind of randomness so that each weight can specialize to different things. Okay. Right. This used to be the big bane of neural networks, overfitting. So, why is that the case? You know, all of you remember what overfitting is, right? Sorry? Yeah, so but, I mean, people remember what overfitting is. Yes? The training examples, right? So essentially you are fitting the parameters very closely to the training examples, so you are not able to do any kind of generalization to unseen examples, right? And the reason why neural networks do this overfitting is exactly because they have too many parameters, right? They have so many weights. So if you remember, we actually counted the number of parameters in a neural network, right? You remember that? M times v plus 1 plus whatever k times m plus 1. So that is a huge number of parameters. So it is very easy for you to overfit, so you have to be careful about it. So there are two ways of avoiding overfitting, right? So can you think of what are the two ways of avoiding overfitting? One we already know, regularization, right? So one way of avoiding overfitting is regularization. So what you do here is you essentially add a quadratic penalty for the weights, right? So you do a norm alpha squared plus norm beta squared, right, and then you try to find the gradient with respect to that, and then you try to minimize things, right? It becomes a little bit more complex, and if you add a squared error penalty, right, if you add a squared error penalty, it is sometimes called weight decay, right, because it makes your weights go towards 0. So sometimes called weight decay. So can you add a L1 penalty? You could add anything. I mean, so it just makes it a little bit more complex. But the question is, does it induce sparsity? Right. So is there another way of avoiding overfitting? Yeah, you can tie parameters together to avoid overfitting. That's good. But then which parameters do you tie together? In fact, one of the ways that deep learning actually has been made efficient is by doing this tying of parameters, right? But then the architectures that look at are very complex, right? So you could tie parameters together and try to reduce those. Okay, so let me put that as a different kind of thing, but it's actually a form of regularizing. But there's yet another approach, which is a purely empirical way of doing things, which is to do what is called validation, right? I actually mentioned this in one of the earlier lectures, right? So you train on a training set and then you have a validation set. I don't, people remember I drew even a picture, right? So as you are training, so the error on your training set keeps going down, right, but the error on the test set or the validation set will initially go down. At some point it will start going up, right, maybe not that dramatically, but go up nevertheless. Like that, right. So the point here is where your right solution is. Okay, so I am putting it in quotes, right solution. Okay, so what is the x-axis and what is the y-axis on this figure? Whatever is your measure of error, it could be misclassification error or whatever, right. So if it's classification, you ideally want misclassification error. If it's regression, it is a prediction error, whatever. And the x-axis is usually iterations, right. But you could also think of having a figure like this for complexity, right. So you could say that I am going to keep adding more and more neurons, right, or more, say I can keep expanding my M, right, I can keep adding more neurons in the hidden layer, right. I can't change the neurons in the input layer, I can't change the neurons in the output layer usually, right, because they depend on the problem that I am solving, right, but I can keep increasing the neurons in the hidden layer, right. but then these are more or less standard techniques for doing I mean for avoiding overfitting, not necessarily tailored to neural networks, right. So you should remember that there was about a decade and a half when people worked a lot with neural networks in between, right. They came up with many techniques for avoiding this kind of overfitting, and they have explored many variations on parameter tying, right, and also many different kinds of regularizing. So there are some really interestingly named algorithms for avoiding overfitting. So one that I particularly like used to be called optimal brain damage. Okay, so essentially the idea was to remove weights from the network, right. So you train the neural network, right, and try to find out the sensitivity of the output with respect to certain weights. Okay, if I am changing this weight, how much do the outputs change? How much does the error change, right? So weights that have low sensitivity or right or yeah, weights that exhibit low sensitivity on the error, right, were then removed, and then you just retrain. Okay, keep doing this. So that way you are removing the number of parameters, reducing the number of parameters heavily, but you are not affecting the output too much. Right. So like that there are many variations on it, but these are the three things, right, that we have to think about. Okay. Related to the overfitting question is the how do you figure out the number of hidden units and layers, right. A very expensive way of doing it is to do a similar validation kind of a setup, right, keep increasing the number of layers and then or number of neurons and check that out. It is incredibly hard, right, and so people came up with automatic pruning techniques, right. People came up with ways of growing your neural network. So they start off by having one neuron, right. So it's something very similar to your forward feature selection, or what is the thing, a stage wise selection, right. So people remember stage wise feature selection. What did you do?
Progressively add the variables, but still we can change some of the variables we added in the
That's stepwise. Stage wise was something different.
Highest correlated variables
With the residual error, right. So you could do the same thing with neural networks, right. You start by training a single neuron, right, and then what you do is once that neuron actually starts making some predictions, right, then you train another neuron that actually nullifies the prediction error, right. Now you add a third neuron that adds up both of these and gives you the output, right. So you could do something like that, right. So you do not have to make a decision as to how many neurons you are going to put in from the beginning, right. As you go along you just keep training more and more, right. But the problem with such a network was that it will not look like your layered architecture, right. I will start off with one neuron, okay, that will give an output, then I will add the other neuron, then they will go. So all of this gets the input directly, then I add another neuron, right. So the layer architecture is gone now, right. So now how many layers does this have, 2 or 3? So this neuron seems to be at the third layer, right, but it is connected directly to a neuron which is at the first layer because it is taking inputs from here. But then well, you do not have to be very dogmatic about having the standard 3 layer architecture. If you remember, when I introduced the standard 3 layer architecture, I said there are a lot of different deviations from this that people have proposed, right, and we will not be looking at most of those in detail. So these kinds of networks where you are actually trying to minimize the residual at every point, they are called cascade correlation networks. So there are so the most statistically sound way is to just do validation. What is the other way to do it? It's kind of a cheat.
guess.
you can do slightly better. What can you do? You are going to kill me. You can take an educated guess. Okay. So it's called using domain knowledge. Right, so you have some information about how complex the system is, and then you can use ideas from that. You can then try to see, okay, one layer, 2 layers, 3 layers, right. So a lot of deep learning network that nowadays happen essentially is more empirically driven. You try one layer, okay, see what is the best you can do, right, see what's the best in performance that you can get, and then you try to add another layer and see if you can improve that, another layer until you are happy that you are performing well, right. Of course, you just can't train the network into the ground, you have to always make sure that you are not overfitting it, but you can still do this, right. Okay. So, I did not explicitly mention this while talking about the neural network training, but you can kind of imagine wherever that I am going to be using the data as it is, right, as a real valued vector, right, I would have to worry about scale, right. So, if I have one variable that has a very large range, another variable which has a very small range, right, the variable with a large range is obviously going to dominate my gradient computation. If you remember, the gradient has a xml component to it, right, that is the input variable is part of the gradient. So, if the variable, some of the variables can have a very large range and some of the variables are going to have a very small range, then the large range variables will dominate the computation, just numerically by being large they are going to dominate the computation, right. So, we do not want that to happen, whether they are actually needed or not, just by being numerically large, right, they will dominate the computation. So, we essentially make sure that all the variables will have the same range, right. So, we talked about this in couple of other scenarios also, but in this case again it is important. So, this is something which people typically forget when they are using either neural networks or SVMs. You take the raw data, right, and you just try to run it through a neural network or run it through an SVM and then produce a classifier, right, and quite often things do not work that well, right. You might find some reported results that are much better than what you are getting by using SVMs. 9 times out of 10, okay. The reason twofold, with SVMs twofold, with neural networks one thing, you forgot to scale the input, okay. With SVMs what happens? So, you have those kernel functions we talked about, right, you forgot to tune the parameters of the kernel function, you just took the kernel function as it is and you are trying to use it, so that the performance will be bad. So, you have to tune the parameters of the kernel function and you have to scale the inputs. If you do not scale the inputs, sometimes the performance can be arbitrarily bad. And this is a problem which SVMs do not have, and that is one of the reasons they became so much more popular than neural networks in late 90s and early 2000s, right. So, the neural network error surface is fairly complex. So, what do I mean by error surface? So, what is, so error surface, what is the x axis, the y axis, the z axis, whatever, can you describe mathematically what the error surface is?
Loss function, how it is curved in few
With respect to what?
all the input
On the what? Parameters, not the inputs, okay. So, the error surface, this is something which people have difficulty, okay, that is the reason I am making a fuss out of it. The error surface is the function of the error with respect to the parameters, okay. So, as I change my alpha and beta, how does the error change, right. So, that is the error surface that we are talking about, right. And so, how does the error surface, how will it look like for the case of SVMs? We are minimizing something quadratic there, right, in terms of beta, right. So, it is actually very nice, quadratic thing. So, it always has a single optima, right. When the optimal hyperplane formulation, the very nice thing about it is it has got one optima, and then if you run an optimizer on it, you will always get that solution, right. The error surface for neural networks, if you think about it, it has got those stupid exponents in there, right. Your sigmoid, the derivative of your sigmoid is in there. So, the error surface is going to look incredibly complicated, right. So, it is going to have lots of little valleys, right. The error surface is going to look something like this. It may even look something like this, okay. So, if I am doing gradient descent, I might come here and get stuck. That looks like, I mean, whatever direction I try to go, the error is increasing. So, I might say, okay, this is the good place to be in. So, I might just stop there, right. I could get stuck here. What about here?
Be slow.
Huh?
Be slow to descend.
Very, very slow or not at all, because the gradient is 0. I mean, if you are in the middle of the point, the gradient is 0 because it is flat. It is flat, I declare that to be flat, okay. So, the gradient is 0 at that point, right, and there you go, okay. And so, you might not just move, right, you are essentially drifting around there, and whatever happens, you are not able to make any progress. So, the error surface can become really complicated like this, right, and this is just on one dimension, right. This is a neuron, this is a single neuron with one input, that is what we have drawn. So, imagine this generalized to a very large dimensional space, right, MP plus MK dimensions, right. So, the surface can be really complex, and again there are a plethora of solutions for getting out of local optima, right. So, we are not going to get into most of those, right. I will just tell you one very practical way of doing it. Essentially do restarts, right. So, you start off with some random initialization close to 0, right, you do gradient descent until you do not change weights very much. Remember those weights, right, remember those weights and remember the performance. Now, reinitialize the network again close to 0, random weights close to 0, use a different random seed please, right, and then rerun the experiments, right, and again you will go off to some other optima, remember those and keep doing it. Okay, there are other techniques which people use, right. So, they can make the, there is something, there are more clever gradient descent techniques, right, which allow you to get over these local optima, not all of them, but at least some of the shallower local optima it allows you to get over easily. So, for example, this is a shallow local optima, right, with a little bit of effort I can actually get over, right. How do you provide the effort, right? So, think of it from a very dynamics perspective. So, people have added something called momentum, right. So, if you have been moving in a particular direction, right, I have been descending little bit, okay, do not stop, just keep going in that direction for some more time, right, that is momentum, right. So, in this case these kinds of shallow things you can get over. So, even though the gradient has slowed down significantly, right, this becomes 0 here, but I will still be going in the same direction I went for a little while longer because I have momentum, it is just going to take me forward. So, that is going to get me out of that little valleys, but if you are in a deep valley then you still can't get out, right. But so these kinds of tricks help, right. Then more recently with all the hoopla with deep learning, right, one of the reasons that deep learning has become so popular now is people do have very powerful gradient based techniques which allow you to navigate the error surface more efficiently. I will not say will allow you to avoid local optima, but it allows you to navigate the surface more efficiently, right. Good. So, any questions so far?
The restarting things work because your random numbers are going to be, might still be near that original optima only, right?
No, why?
No,
Because I am going back to my zeros.
yeah, but your weights you want them to be small again. So
Yeah, when I restart, it will again be small weights, right? I will be very far away from this. This optima I have converged to after a lot of training.
yeah, but I'm saying that you might still reach that same
Maybe not. See, this is one thing which you should get your hands dirty, then you will see what I mean. Even small changes in the starting weight configuration can lead you into very different optima. The error surfaces are so complex, right? And remember, I am not just moving in one direction or the other, I have a very large dimensional space in which I am moving, right? So even though I am constraining it to be around 0, right, the volume that I can actually start in is very large because of the high dimensionality of the weight space, right. So and each random starting point can be very different. Of course, it is also possible that you start in the same location or start very close to the same location and end up with the same optima, but the probability of that happening is very small, especially with large networks. So if you do the restart, you will actually end up somewhere else, right. Any other questions? So we have till this point we have for the exam, right, tomorrow? Just checking.
The absolute minima itself is flat, then how do you know whether to restart or
Yeah, so that is the question nobody asks. How many times do you restart? Right, I mean you have a budget, you just say that okay I am going to restart this many times, right, and yeah, you might have actually reached absolute minima, but you must still be doing restarts. That is one of the reasons I told you to remember the weights, right. It could very well be that the best solution you got could have been the first one, right, and all the few further restarts that you do could actually be leading to worse solutions, right. So I am not guaranteeing that if you do a restart you will get a better solution. The restart just allows you to explore different local optima and pick the one that is best.
What if it's very costly to do this?
Then don't, right. It all depends on your budget, right. I mean if it's as expensive as to train the network the first time around, right, and it is really expensive to train the network if you are doing deep neural networks, because the number of parameters are really large, runs into several hundred thousands, right, and therefore doing a restart is expensive. We do fewer of them, and I also try to come up with other gradient descent techniques which allow you to avoid local optima, right. So the whole idea behind simulated annealing is that you would want with some probability of ignoring the gradient, right. So what the whole algorithm here says, at every point follow the opposite direction of the gradient, right, you descend the gradient direction, right, you find which is the maximum ascent direction, you descend it, right. The whole idea behind simulated annealing is to say that no, I allow you to ignore the gradient, okay, you can move in another direction, in fact you can move in the direction of the gradient also if you want, right. So the gradient, opposite direction of the gradient is a choice that is given to you, right, you can choose that or you need not choose that. As the number of iterations become larger and larger, the probability of you choosing the direction of the the gradient direction is going to become higher and higher, right. So this is essentially what we call the temperature parameter. The temperature parameter, if it is very high, right, is you can think of this particle that is going to be jumping all over the place, right. So if the temperature is very high, you can move in whatever direction you want, you are not necessarily constrained to following the gradient direction, right, and as the temperature becomes lower and lower, then you are constrained to follow the direction of the gradient. So the reason it is called temperature is because it is actually used in modeling physical systems, right. So if you look at the Boltzmann distribution, which people typically use in this context, that is actually a parameter called temperature, which behaves very much like this, right. So one other way to think of what simulated annealing will do to your error surface, it is like it will pull your error surface taut, right. If the temperature is very high, it is like your error surface is flat. It essentially means I do not have any gradient information, I can move any which way I want, right. Whatever direction I move, it looks the same, right. I can just move randomly, right. And then what happens, I slowly start regaining the shape of the error surface. So what will happen is, first the deepest dink will form, okay, the shallower ones will still be farther away, and the deepest thing will the first dip that will appear in my error surface, and likewise as I keep cooling it will completely go back to the original error surface, okay. That is one visual way of thinking about it. I mean, there are more formal ways of explaining why that visualization works, right, but I do not want to get into simulate annealing today, but that is another way of avoiding local optima, okay, done.